with you again. Right. So the next lecture 21 is using this idea of reducing a number or the modulus of a number, just taking a little bit further. And you can see where this is going. Because remember Caesar's cipher was, we start with, it started with E, which was the fifth letter of the alphabet, and we moved forward by 3 to get E, F, G, H. So this idea of reducing a number is going to be useful, because if you take something towards the end of the alphabet, like Y, which is the 25th letter, and you move forward 3, you get to 28. And what's the 28th letter of the alphabet? Well, there isn't one. So what you do is you wrap around and you say, well, in fact, you're thinking about the second letter of the alphabet in the MAT1MIT system. So Y ends up being encrypted as B, which, let's see, where is it? Yep. So there's Y gets encrypted to B, wraps around the clock face. Okay, so that's basically where we're going. So let's do this. As I said, this whole area is an area of mathematics called number theory, which is what it says. It's a theory of numbers, meaning integers. And we're going to use these ideas to look at very simple ideas in cryptography, but really sophisticated things, which is a part of number theory, relates to something called elliptic curves. And elliptic curves is one way of doing cryptography, or one tool that you can use to create secure cryptographic schemes using these things called elliptic curves. And to get to elliptic curves, we basically start with these ideas, and you spend about 2 years studying this sort of stuff before you get to elliptic curves. So this is really quite sophisticated mathematics. Maybe not 2 years, but I mean, it's not. If you started with these ideas of reducing a number, this modular arithmetic, it will take you several months, a year to get to this sort of thing. So we're just scratching the surface, but it's worthwhile knowing that, even though we're doing very simple things, they are very important for how things work, because you couldn't get to these more sophisticated techniques without starting with these. You have to start somewhere. So just to recap, 19 is congruent to 3 mod 8. Why? Because the difference is 16. 19 minus 3 is 16, which is 2 times 8, so a multiple of 8. 24 minus 7 is, 17, and 17 is not a multiple of 5, so they're not congruent. So 91 is reduced to 3 modulo 8. Okay, well, there's a couple of ways you can do this. You could, first of all, just sit down and think, so modulo 8. So 91, we're looking at mod 8. And if you knew your 8 times table, you think to yourself, well, 8 11s, straight away, 8 11s is 88. No, I should do it this way. 11/8 or 88. Doesn't really matter which way around you do it, though. So I'm trying to do the multiples of the modulus there. So 11/8 or 88. So you straight away say that 91 is 88 plus 3. 88 is, just to emphasize it, is a multiple of 8 plus 3. So 91 mod 8 is equal to 3. So pretty straightforward. This relies on you knowing your 8 times table. Here we're going to do a slightly different technique. Large numbers, which are easily factorized, can be sometimes reduced more quickly. And let's do an example here. Just to show you how it works. We take 300 mod 14. So I want to reduce 300 modulus 14. How would I go about it? Well, again, the tedious way would be 1 14 is 14, 2 at 28. What happens next? 3 lots of 14 is 42, and you just count down till you get a multiple which is just under 300. Or you could say 300 divided by 14, use your calculator to work out that. Or, and here's another way, what you notice is that 300 is easily factorizable. So 300 is actually 30 times, 30 times 10. So when we're asking for 300 mod 14, we've actually got 300, and we want to reduce mod 14, is 30 times 10 mod 14. And here's a neat bit. 300, which is 30 times 10, if I want to reduce that mod 14, I can do the following thing, which kind of looks obvious, but does need a bit of explanation. I can simply take 30 mod 14, take that one, and multiply it by 10 mod 14. And that's a whole lot easier, because I know that 28 is a multiple of, is the multiple of 14 just under 30. So 30 mod 14 is actually 2. Okay, why? Okay, 30 is equal to 2 times 14 plus 2. So there's our remainder 2. 10 mod 14, well, 10 is already under 14. So that's 2 times 10. Should have kept these congruences in here. Two times 10 mod 14 is 20 mod 14. And 20 mod 14, well, that's easy. That's, well, 14 from 20 is basically just 6. That was pretty neat and straightforward. If you can factorize this number easily and reduce it into smaller things, then all you have to do then is work out what each of the smaller things are reduced by the same modulus and multiply those together. And there might be an extra step, so 2 times 10 is 20, but that's pretty easy to do mod 14. That's what's happened in this one, in this particular slide, reducing 300 mod 14 without using a calculator. Now, this is the neat bit. 300 is 30 times 10. So 300, and I wrote this out a little bit awkwardly, but this is a better way of writing it. 300 is 30 times 10. And the point about this is that 30 and 2 are actually the same thing in the mod 14 arithmetic. So if you start with 1, 2, 3, all the way around to 14, and you keep on going around, so that's 15, 16, and you keep on going all the way around, and you get to 30. 30 and 2 are basically the same object in this arithmetic. So wherever I see 30, I can actually replace it by 2, because we're doing this congruence or equivalence. 10's around here. There's nothing simpler than 10. So this idea is that 30, by factorizing into 30 times 10, I'm actually using this very neat idea that 30 is actually the same thing as 2 in that system. So wherever I see 30, I can replace it by 2 in that system. And since I'm reducing mod 14, where am I here? It's the same thing. So I can set it out this way using, instead of equal signs, so 30 is not equal to 2, it's equivalent or congruent. That's why we've got the 3, the triple equals there. So 300 gets reduced to 6 mod 14. And what's going on here is that if, this is what this is really saying, if you have 2 numbers which are congruent and 2 other numbers which are congruent using the same system, then multiplying these 2 is the same as multiplying those 2. Or if you just want to think about it this way, if 2 numbers are congruent, wherever I see 1 in the calculation, I can replace it by the other one in the calculation, as long as I keep these congruent symbols going. Now, I'd like to get you to think about this. What would happen if instead of 30 times 10, we'd done 20 times 15? So what I'd like you to do is start out 300 equals 20 times 15 and follow the same steps and see what happens. So I'll give you a minute on that. Okay, let's continue. Just going back to the, where am I? Just going back to the 30 times 10 one. Look, this is a slightly better way of writing it out. So I sort of garbled my way through here. Here's a better way of writing it out. 300 is congruent to 30 times 10, simply because 300 is 30 times 10 in the mod 14 system. So if you keep on writing this, to remind yourself from each step that you're doing that 30 in the mod 14 system is the same as 2. So 30 and 2 are the same thing, or congruent to each other. So 30 times 10 mod 14 is the same thing as 2 times 10 mod 14, which is 20 mod 14, which is congruent to 6 mod 14, because you can do that in your head. If you follow the same sort of template, 300 is 20 times 15 mod 14. What's 20? Oh, we already worked that out. That's 6. So in the mod 14 system, 20 and 6 are the same thing. What's 15 equivalent to? Well, it's just 1 more than 14. So it's equivalent to 1. So we've done the same thing. 6 times 1 is 6. You can't get any simpler than 6 in the mod 14 system. And we get the same answer. So it's a really neat trick. And I think this way of setting it out is really, really helpful, because it just reminds us that 30 and 2 are actually equivalent in this system. 20 and 6 are equivalent. 15 and 1 are equivalent because they have the same remainders. The other thing you can see is 15 minus 1 is 14. 20 minus 6 is also a multiple of 14. Okay. So here's another example, 1800 mod 27. Let's use the factorization 6 times 30. So remembering that we're doing this mod 27. Okay, so 60 mod 27 is actually 6, and 30 mod 27 is 3. That one's easy to see. That takes a little bit more work. So remember, this is in the mod 27 system. 6 3s are 18, mod 27. 18 is as simple as you can get because it's between 0 and 27. So 18 gets reduced to 1800 gets reduced to 18. And you can see that's really, really simple. What if you did 60 times 30? Instead of 60 times 30, suppose you saw that 1800 is 90 times 20. Well, in that case, you've got 1800 is congruent to 90 times 20 in the mod 27 system, and that's congruent to, let's see, now I've got to do a little bit of arithmetic myself. 3 times 27 is 60, 81. So that's 9. Okay, I'll leave you that. I'll leave you to check that 90 and 9 are congruent to each other in the 27 system. Times 20, there's not much you can do. Mod 27. So that's congruent to 180. Mod 27. And, well, okay. What could you do now? You could perhaps do, well, 18 times 10 would work, but that wouldn't be very helpful. What would be something a bit simpler? Suppose you did 90 times 20. 30 times 3. 30 times 6. Mod 27. Okay. 30 is equivalent to, well, from 27, that's just 3. And 3 times 6 is 18. So while this method does make life easier, if you choose the wrong factorization to start with, it takes you a few more steps than other factorizations. So the trick with this one, 60 by 30, is that you get 2 small numbers to begin with, whereas this one, 20 was not very good because it didn't get reduced, whereas 90 did get reduced, then you had to do some more work. But you still get there on the end. Okay, oh, here we better get cracking along. So reducing powers. So suppose I ask you 2 to the 12. What's 2 to the 12? 2 to the 12 is 2 to the 10 times 2 to the 2. 2 to the 10 is 1,024 times 4, which is 4,096. Okay, so 4,096 modulo 7. Now, what you notice here is that I began with, what is 2 to the 12? And I've got 4,096. Now, while that's true, it isn't absolutely necessary to do that. What you could do is, and this is what's happening here, let's take 2 to the 12, and that, without working out what it is, let's see if we can factorize it into something a bit simpler without actually knowing that it's 4,096. And the way to do it is, if you realize that 2 cubed is really 8, and 2 to the 12 is 2 cubed times 2 cubed times 2 cubed times 2 cubed, right? Because 3 plus 3 plus 3 plus 3 is equal to 12. And if you realize that 8 is congruent to 1 mod 7, then life becomes really, really easy, because what you see is that your original number 2 to the 12 is 2 cubed times 2 cubed times 2 cubed times 2 cubed, which is 8 times 8 times 8 times 8. Okay, so this is in the mod 7 system. And this is still in the mod 7 system. 8 is equivalent to 1. 8 is equivalent to 1, 1, 1. And what's 1 times 1 times 1 times 1? It's 1 in the mod 7 system. So without even working out what 2 to the 12 is, we can reduce that to 1 mod 7 with a bit of creative thinking here. Okay, what about 3 to the 8 mod 25? So here what we could do is 3 to the 8 is 3 cubed times 3 cubed times 3 squared. Okay, because 3 cubed, you know, is 27. And 27 mod 25 is just 2. So basically you're thinking of what power of 3 gets you just above 25. So 3 to the 1 is 3, 3 squared is 9, and 3 cubed is 27. So 27 is just above 25. So if we factorize using 3 cubed, so 3 to the 8 is 3 cubed times 3 cubed, and then with another 3 squared left over. So that 3 plus 3 plus 2 is 8. Okay, so in the mod, just to emphasize this is all done in the mod 25 system. 3 cubed is 27, 27, 9. 27, 27 are both equivalent to, remember these are equivalents, equivalent to 2. You can't do much about that. 2 2s are 4, times 9 is 36, but 36 mod 25 is easy, that's just 11. So without calculating what 3 to the 8 actually is, you've worked out. Okay, well, maybe, I mean, there's some answers here, just to break things up a bit. Maybe you could work on number 2 and then number 1, just see how you go. I'll just give you a minute to think about it. Okay, let's just stop and do number 2 as a quick little exercise. So here we go. 2,500 is 50 times 50. Okay, 5 times 5 is 25, times 10 times another 10 is 2,500. So 2,500 is congruent to 50 times 50 mod 42. And we recognize that 50 is one lot of 42 with 8 remainder. So basically 50 is congruent to 8. So what's 8 times 8? 64. So 2,500 is congruent to 64 in the mod 42 system. And because 64 take away 42 is just 22, that's 22 is the remainder. So we end up with 22 as our answer, which is what was wanted there. I'll skip number 1 because we'd better get cracking on to the Caesar cipher. Okay, so going back to Caesar cipher. In that particular one, we moved forward 3 letters, and wrapping around. So going around the clock, going around clockwise on the clock face, the letter clock face. Where is it? I've lost it. I've lost it in 2 minutes. Just bear with me because I do want to find it. There we go. Yeah, so there's our clock face. The Caesar cipher means shift forward 3. So E becomes H. Y becomes 1, 2, 3, becomes B. So bearing that in mind, that idea of wrapping around, if we do the following, remember that lowercase we're going to identify with the plain text, and uppercase we're going to identify with the ciphertext, except here, this is a little bit different. So if we say A is 1, B is 2, C is 3, Z is 26, and so we convert the letters to numbers, and then we do arithmetic to that. So basically we take the plain text number, so this is what P is, the plain text number, and we add 3, do the mod 26, then that tells us what our ciphertext number is. So plain text N is the 14th letter of the alphabet. We take 14, we add 3, that gives us 17, and whatever 17 is, mod 26 is the number for our ciphertext. So 17, what's the 17th letter of the alphabet? You'll actually get these in the test, so you don't have to worry about writing it out, but you'll get these in the test. What's the 17th letter of the alphabet? Well, N is the 14th, 15th, 16th, 17th. So basically Q. So the 17th letter of the alphabet is Q. So N is encrypted as Q. But notice that we're doing the arithmetic on the letter or the numerical equivalence. So plain text N is the 14th letter. That gets transformed by this formula into the 17th letter, and that's what we look up the 17th letter as Q. Okay, now to illustrate that wraparound principle, okay, let's encrypt the letter Y. Okay, where's the letter Y? Y is here. Y is the 26th letter of the alphabet. So what we do is we... who saw my mistake? Yeah, thanks. 25th letter of the alphabet. Z, of course, is the 26th letter. So Y is the 25th letter of the alphabet. So basically you say to yourself, Y is 25. We take 25 plus 3, which is 28. But remember, we've got to do everything in the mod 26 system because there are only 26 letters. 28 reduced in the mod 26 system gives us 2. What's the second? So 25 plus 3. 25 plus 3 is equivalent to 2. What's 2 in the system? Well, the first letter is A, the second letter is B. So just remember that we use capitals for, so this is the plain and this is the ciphertext character. So C, so in this case, this is P, a plain text number, which represents our plain text character. Do something to the plain text number, P plus 3, congruent to 2. 2 is our ciphertext. So that's C. This C is a number, but that B is an actual character. C is number 2. What's the second letter of the alphabet? B. So, should say. Let's see there. So Y gets encrypted to B. So basically, you're just reducing the final number, so it's between 1 and 26. Now, the only trick here is that 26 is actually congruent to 0. So really you're going from 1 up to 25 and then 0. But just for convenience, because we tend to think of A as being the first letter, B as being the second letter, Z as being the 26th letter. Most people are more comfortable at starting counting at 1 and going up to 26. If you started with 0, I mean, you could think of that as being 0 as well. It wouldn't hurt. So how do you decrypt? Well, if you take a plain text number and you add 3 to get your ciphertext number, how do you go from a ciphertext number to the plain text number? Well, you subtract 3. So the trick is, the decryption algorithm is, the person at the other side takes a ciphertext number, subtracts 3, works out MAT1MIT, and that's the plain text number of the character. Which is obviously the reverse of the encryption. Encryption is adding, the reverse is subtracting. Remember I said something like this. A bit of paper. Remember I said something like this. Where is it? Here's a clock face. That's 1, 2. Remember I said something like this. If I start at 2 and I subtract 4 hours, what happens? I go backwards. 1, 2, 3, 4. So I start 2, I subtract 4, gets me back to 10. That's exactly the same thing as going forwards, 1, 2, 3, 4, 5, 6, 7, 8. So starting at 2 and going forwards and ending at 10 is the same thing as adding 8. Now, this is really important. What this is basically saying is that subtracting 4 is precisely the same thing as adding 8 in this 12-hour clock arithmetic, just as far as the numbers are concerned. Adding 8 is exactly the same thing as subtracting 4. And that's exactly what's going to happen here, that to do the deciphering, we subtracted 3. But another way of doing that is to add 23. So if you take, where we go from, let's say we're going from Y, let's say we're starting at B and we're subtracting 3. What happens? We get to Y. So if we start there, we end there to decrypt. That's exactly the same thing as adding 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So subtracting 3 is the same thing as adding 23. You get to exactly the same spot. Doesn't matter where you start. If I start at I and subtract 3 to F, that's the same thing as starting at I and adding 23 to get to F. Why does that work? Well, basically because 23 plus 3 is 26, or more to the point, 26 minus 3 is 23. So here's an alternative decryption formula. Instead of subtracting 3, we can simply add 23. Why? Well, what's going on here is that the plain text is congruent to the cipher text minus 3. This is in the MAT1MIT system. That's congruent to C minus 3 plus 0. So if I add 0, I don't do anything. And 26 in, 0 in the 26 system is the same thing as 26. So 0 and 26 are the same. And minus 3 plus 26 is plus 23. So this is the formal way of justifying that the original encryption, the original decryption technique is actually the same as, of subtracting 3 is actually the same as adding 23. So either think about it in terms of this. So subtracting 3 is the same as adding 23. So if I want to decrypt J, J is the 10th letter in the alphabet. I do 10 plus 23 is 33. 33 is congruent to 7, so 33 is actually 7. And I translate that back into the 7th letter of the alphabet as J. Remember, we're decrypting, so the ciphertext is capital. It's the 10th letter. If I subtract 3, I get 7 automatically. But if I add 23, I get 33. The 33 is the same as 7. And so I can translate that back to lowercase g for the plain text character. Now, the Caesar cipher relied on always shifting 3 forwards to encrypt, 3 backwards, or 23 forwards to decrypt. And there's really nothing special about the 23. The only reason it's of any historical interest is apparently that's what they actually used. But you could shift forward 1 spot, or 10 spots, or 11 spots, or 25 spots, or you could shift back 3, or you could shift back 7. So there are actually 26 different ciphers of this Caesar type. And when we say a Caesar type cipher, we mean shifting forward or backwards to encrypt and decrypt. So your shift could be 1 place forward, so A becomes B. Yeah, so A becomes B, B becomes C. That'd be a shift of 1 spot. Sorry, I've got a cough. Sorry about that. So you could shift forward 1 spot. Y would become Z, and Z would become A. Capital Z would become little z would become A. Or you could shift 2 spots, so A would become C, B would become D, Y becomes Y would become A, and Z would become B. Or you could shift forward 3 spots, or 4, or 5, etc., etc., etc. You could shift forward 26. What would happen if you shifted forward 26? Well, B would become, shift forward 26, B would become B, which isn't very interesting. It's the same as not shifting at all. If you shifted forward 27 spots, B would become C, which is just the same as shifting forward 1 spot. So really, there are 26 different ciphers where you shift forward that many spots. So we can have a more general thing. Instead of using add 3 to get the cipher text letter, you could have an arbitrary shift of B. So when B was equal to 3, plain text character number plus 3 gives you the ciphertext character number. In general, that shift forward, so that shift forward can be anything, could be 5 or 25 or 13 or 7. And of course, if you shift forward that amount to decrypt, you're going to shift backwards, you're going to subtract. So when we added 3 in the Caesar cipher, we had to subtract 3 to decrypt. And another way of writing this is to decrypt is you take the ciphertext character and you shift forward. Instead of shifting back by B, you shift forward, you add by 26 minus B. So when we had 3 there, you either subtracted 3 or you added 23. They were equivalent. So if B was, suppose 6, suppose I wanted to shift forward 6. How do I decrypt? I shift backward 6, which is the same thing as shifting forward by 26 minus 6, which is 20. So shifting back 6 is the same thing as shifting forward 20. So here's a really quick example. Shift of 15 positions. So this is saying the shift value was 15. So T is the 20th letter. So we take the 20, add 15. It's congruent to, well, it is 35. Reduce that to 20 in the mod 26, so that's 9. What's the 9th character in the alphabet? It's capital I. Okay, so T gets encrypted to capital I. Okay, how do you decrypt D? Remember uppercase for cipher. So D is a 4th letter. We take the 4th letter and instead of shifting backwards by 15, we shift forwards by 26 minus 15. So 26 minus 15 is 11. We add 11 to that, we get 15. What's the 15th letter of the alphabet? It's 0. O. So D gets decrypted to O. Now, you might wonder, why are we doing this odd thing of decrypting by adding 26 minus the shift? Well, the reason being is if we did 44 minus the shift, 4 minus 15, 4 minus 15 is negative 9, negative 11, I can't count. So 4 minus 15 is negative 11. And most of us are not very good at doing negatives in the mod system. So I'd have to ask myself, where is negative 11 if I had to reduce it? So this is why, I mean, it's doable, but it's just an extra step. This is why when we add something, we don't go negative, or don't have the possibility of going negative, and then it's a little bit easier to deal with. So it turns out that negative 11 is actually equivalent to 15. You can see that because 15 plus 11, or you can see that because 26 minus 15 is 11. Okay, so these are what are called additive ciphers, where you're simply adding a fixed amount to each letter value to do the encryption. And the important thing is that it's the same fixed amount each time. So if I ask you, and that's not very secure, so if I said, YWHH is an unknown ciphertext. It's been shifted by a certain amount from the plain text. Well, it wouldn't be very difficult just to try every possible shift to decrypt it. So if you start with YWHH and just shift forward one step at a time, so Y becomes Z, W becomes X, H becomes I, Does that work? No, not really. So let's shift again by the same amount, because remember, all these letters have been shifted by exactly the same amount. So if we shift them all by 1 or by 2 or by 3 or by 4, we end up with what is possibly the plain text. So we've got a pretty cluey idea that 22 is the shift to create. So if you say C-A-L-L, and you shift by 22, that gets you to YWH. So it's really easy to crack. And basically, you're using brute force. You're just trying every shift, so called brute force, or sometimes trial and error. We'll have a look at this next time. Okay. This is actually starting to get pretty interesting stuff, I reckon. Where are we? Sorry, I meant to finish a little bit early, but this did take a little bit longer. So we'll meet tomorrow, start looking at the problem sheet, and we'll meet tomorrow at 10 o'clock, see how you go with it. As I said, this is starting to be the more interesting end of the